This is Section 2-5, Part A, Rational Functions. The I can statement for this section: I can analyze and graph rational functions, and I can solve rational equations. For Part A of this section, we're just going to work on the I can statement of analyzing and graphing rational functions. So a rational function is the quotient of two polynomial functions, a of x and b of x, where b is a non-zero polynomial. The domain of all real numbers, excluding the zeros of b of x, is what we'll use for our domain of our rational functions. Now, a rational function is that f of x is equal to a of x over b of x. A of x is a polynomial function, so it's a sub n times x to the n power, going on until we get to a sub 1 times x to the first, plus a sub 0, where a sub 0 is your constant. Your b polynomial, b sub x, we're going to say that's b sub m times x to the m power, so it has a degree of m, going all the way to b sub 1 times x plus b sub 0. So the degree of your polynomial a of x is going to be an n, and the degree of your b of x will be m. Now we're going to look at asymptotes. An asymptote is a line or a curve a graph approaches, but it's never actually going to reach it and it will never touch it. We have three different types of vertical asymptotes we're going to look at today. Three different types of asymptotes to look at. The first one is a vertical asymptote. This is going to be a line of the form x is equal to c. It'll be a vertical line on the graph that it's approaching but never touches. We find our vertical asymptotes by finding all of the real zeros of the b of x. So you're going to find all the zeros of the denominator. Anywhere you have a 0 in the denominator will be a vertical asymptote. Horizontal asymptote has a couple extra rules. It's going to be a line of the form y is equal to c. And again, it's going to be a horizontal line that it approaches but never touches. To find the horizontal asymptote, you first have to look at the degree of a of x and look at the degree of b of x. If the degree of a of x is less than the degree of b of x, then we're going to have a horizontal asymptote at y is equal to 0. If the numerator and denominator have the exact same degree, we're going to have a horizontal asymptote at y is equal to a sub n over b sub m. Remember, a sub m is your leading coefficient for your numerator, and your b sub m is your leading coefficient for your denominator. And in the case where n is greater than m, the degree of the numerator is larger than the degree of the denominator, there will be no horizontal asymptote. Now, if the n value is greater than the m value, we could have an oblique asymptote if the degree of the numerator is exactly 1 more than the degree of the denominator. And to find the equation of that oblique asymptote, you are going to divide a of x by b of x, and the quotient of your polynomial will be the equation of your oblique asymptote. We're also going to look at some intercepts. We have the x-intercepts. This is where it crosses the x-axis. To find your x-intercepts, you just need to find the zeros of your a of x or the zeros of your numerator. To find your y-intercepts, we're just going to plug in 0 for our x, because we have a y-intercept when x is equal to 0. So if we plug in a 0 for all of our x's and solve, that'll tell us where our y-intercept is located. We can also have holes in our graph. This just means it's a removable piece of information. The graph is continuous to the left and the right of it. That piece is just missing from the graph. And we know we're going to have a hole if we have a factor or a 0 that is in the numerator and the denominator. So an example of this would be f of x. If you look at the numerator and the denominator, both of them have an x plus 3, which has an x value of -3, because remember, when you pull it out of the parentheses, you change the signs. So we would actually have a hole in our graph where x is equal to -3. It won't be an asymptote, even though it's in the denominator, because it is a hole. Since it's in the numerator as well, it's a hole instead of an asymptote. So if we take a look at some examples, the first thing you need to do is always make sure your function is factored all the way down. Then we're going to look at the degrees, and we're going to look for the asymptotes, intercepts, and wholes. So for this function, it's already factored down, so that's going to help us. We're going to start with our asymptotes. We're going to look at vertical asymptotes first. Your vertical asymptotes are the zeros of your denominator. So our denominator is x plus 3. If x plus 3 is equal to 0, when we get the x by itself, we'll have x is equal to negative 3. So this means that we have a vertical asymptote at x equals negative 3. We're going to go ahead and graph that onto our graph. So we go over to where x is negative 3, and we will put a dotted vertical line. This is the line that our graph is going to approach from the left and the right, but it's never going to touch. Next, we're going to look for horizontal or oblique asymptotes. So we need to look at the degree of our numerator, the degree of our denominator first. Because our numerator doesn't have any variables, we have a degree of 0 because there is no variable. Our denominator has x to the first, so this has a degree of 1. Now, if we remember back to our rules about horizontal asymptotes, if the m is greater than the n, so the denominator has a higher degree than the numerator, then we will always have a horizontal asymptote of y is equal to 0. So we have a horizontal asymptote of y equals 0. Again, we're going to put this onto our graph. Next, we're going to look for the intercepts. We have an x-intercept when we have the zeros of the numerator. If you look at the numerator, we just have 6. There's no variable to solve for. So since there's no variable, we can have no x-intercept. This also should make sense because we have an asymptote across the x-axis, so it cannot touch the x-axis. To find the y-intercept, we are going to plug in 0 for all of our x's and then solve. So when x is 0, y is 2, so we have a y-intercept of 2. So if we go ahead and graph our y-intercept onto our graph, we're just going to go up to 2 and put a dot. Next, it says to look for any wholes. You only have a whole if you have a factor that's the same on the numerator and the denominator. So in this case, there are no wholes. Now we need to graph the function. So we know what it's approaching, we have one of its intercepts, but we don't know where else it's going. To do this, you're going to make yourself a table of values and then place them onto your graph. So in our table, we're going to find values. So you pick x values that are going to fit on the graph. So we went from x values of -5 up to 3. Then we're just going to plug those x values into your equation and get each y value. If you notice at -3, it is undefined because that's where your vertical asymptote is located, so there cannot be an x value. With the x value, there can be no y value. Now we're just going to go and graph these points. So at -5, we're at -3. At -4, we're at -6. So this tells me I know I have to get close to the red line and close to the blue line. So apparently I'm getting close to the blue line in this direction, and we're going to get close to the red line in this direction. At -2, we are at 6. At -1, we're at 3. 0, we were already at 2. 1, we're at 1.5. 2, we're at 1.2. And at 3, we're at 1. Again, we know we have to get close to the blue line and never cross it, and close to the red line. So this will be our graph. The last thing we would do is state the domain. The domain of the function is finding me where it cannot happen. This will be any holes and any vertical asymptotes. We have a vertical asymptote at x equals -3, so our domain x cannot equal -3. If we take a look at this function, before we can start, we do need to factor it down. So if we factor out a 3, we're left with x squared minus 1 over x squared minus 9. If you notice on the numerator, x squared is a perfect square and 1 is a perfect square. Since this is subtraction, we can factor this. This is a perfect square. It's always going to be 1 plus 1 minus. The square root of 1 is 1 and 1. On the denominator, we do have the same thing. X squared is a perfect square and 9 is a perfect square. Since this is a minus, again, we can factor. 1 will be a plus, 1 will be a minus. The square root of x squared is x. The square root of 9 is 3. Now that we have factored down, we're going to look for any holes and any vertical asymptotes. If you notice, there are no factors of the same on top and bottom, so there are no holes. For vertical asymptotes, you're just looking to find the zeros of the denominator. Remember, when you pull them out of the parentheses, you change the sign. So we are going to have a vertical asymptote at x is equal to -3. And we're going to have another vertical asymptote at x is 3. Now we need to look for horizontal asymptotes. So we need to look at the degree of our numerator and the degree of our denominator. On our numerator, we have a degree of 2. On our denominator, we also have a degree of 2. If we come back and look at our rules about horizontal asymptotes, when the degrees are exactly the same, then we have a horizontal asymptote at y is equal to a sub n over b sub m. So that means you're going to take your leading coefficient of your numerator over the leading coefficient of your denominator. So in this case, our leading coefficient of our numerator is 3. Our leading coefficient of our denominator is 1, because there's 1x squared. So our horizontal asymptote will be at 3 over 1, or it'll just be at 3. So we'll come over to our graph, and we'll graph a horizontal line at y is equal to 3. Next thing we need to do is we need to check for intercepts. Remember, the numerators, the zeros of the numerator, will be your x-intercepts. So in our numerator, we have the zeros of, if I pull out the first one, it's going to become x is equal to -1. And the second one, if we pull that out of the parentheses, it's become x is equal to +1. So we're going to cross the x-axis at -1 and +1. To find the y-intercept, we're going to plug in 0 for our x's and solve for y. So if we go back to our original function, this is going to give us -3 over -9. Or if we reduce that, that'll just be 1/3. So we have a y-intercept at +1/3. Now the center of this graph we can kind of figure out before we even make our table. We know it cannot approach or touch that red line, so it's going to have to go away from the red line and stay away from the blue lines. So if I'm here, we know our graph is going to have to go down. But we do need to find values outside of those blue lines. So to the left of the asymptote of x equals -3 and to the right of the asymptote of x equals 3. So we do need to make ourselves a table. So if we pick values that are to the left of our asymptote on the left and to the right, that'll tell us what direction the graph should be going. We do know to be approaching the blue and the red lines, so that will give us an idea, but we need to know if they're going to be above the red line or below the red line. So we are going to plug in values. If you put your original equation into your y equals, you can then find the values by going to vars, y vars, and function, and then plugging in your value to fill in our table. So once we fill in the values in the table, we can graph the points. So at -5, we're going to be at 4.5. And at -4, we'll be at 6.4. So we know it's getting closer to the blue line in this direction and closer to the red line in this direction. On the other side, we know 4 is at 6.4. And we know 5 is at 4.5. So again, it's going to approach the red and blue lines. It's going to approach the asymptotes but never touch it or cross it. On this function, we do need to factor out the denominator first. Hold on, we need to go back for 1 second. We forgot to state the domain on this problem. So if we state the domain, remember it cannot be any holes or any vertical asymptotes. So our domain in this case will be x cannot equal -3 and x cannot equal 3. So on this function, again, we are going to have to factor out that denominator first. We want to see what multiplies to get -12, that adds to get a +1. That'd be a +4 and a -3. Because 4 times -3 gives us -12, but 4 plus -3 does give us a +1. Now we're looking for any holes or any vertical asymptotes. There are no common factors in the denominator and numerators. There are no holes. But for vertical asymptotes, we're going to look for the zeros of the denominator. Remember, when you pull them out of the parentheses, you change the sign. So we're going to have vertical asymptotes at x equals -4 and x equals +3. Next, we're going to look for horizontal asymptotes. We need to determine the degree of the numerator and the denominator. The degree of our numerator is 3. The degree of our denominator is 2. So if we look back, when the degree of the numerator is larger than the degree of the denominator, there is no horizontal asymptote. But because the degree of our numerator is exactly 1 more than the degree of our denominator, there will be an oblique asymptote. So we're going to have to solve for that oblique asymptote. To solve for an oblique asymptote, you're going to go back to your original function, and we're going to divide our numerator by our denominator. We are going to have to do this with long division. Remember, if they do not give you everything in descending order, you do need to put in zeros to fill in the spots. Now we need to see what I need to multiply x squared by to make it look like 2x cubed. We need to multiply by a 2 to get the number out front to be correct. We're at x squared, we need x cubed, so we need one more x. So we're going to multiply by 2x. Remember, you're going to multiply that 2x by each piece out in front. So 2x times x squared gives us 2x cubed. 2x times x is going to give us 2x squared. And 2x times negative 12 gives us a negative 24x. Now we do subtract down. A lot of people have issues with our signs in this case, so when you're subtracting down, we can change this and say we're adding, but then change the sign of every piece. So 2x cubed minus 2x cubed gives us 0x cubed. 0 minus 2 gives us a negative 2x squared. 0 plus 24 gives us 24x. Then we're going to bring that 0 straight down. What do I need to multiply x squared by to make it look like negative 2x squared? We're going to multiply by negative 2. So this is going to give us negative 2x squared minus 2x plus 24. We are going to have a remainder left, but we're not worried about that part. We just carry about the quotient part of this, so we just care about that 2x minus 2. So that will be our oblique asymptote. So when we graph your oblique asymptote, you will go to negative 2, put a dot, and I have a slope of 2, so up 2 over 1. And we will draw a dotted line that goes through this. Now, for our graph in here, it's actually not going to affect it much because of the scale, but I'll show you where it will later. Remember, next you find the intercepts. Your x-intercepts is where the numerator is equal to 0. So 2x cubed is equal to 0. If we divide both sides by 2, we get x cubed is equal to 0. Take the cube root. X is just equal to 0 will be our x-intercept. And the y-intercept, you plug in 0 for the entire function. If we do this, it's going to be 0 over negative 12. So in this case, our y-intercept will also be 0. Now if we find some extra points and put them onto a table, we are going to see that we have a value when x is negative 3 of 9, so we can put that on our graph. And we're going to see if we plug in a value of 2, that we have a value of negative 1.6. So the inside of our graph is going to approach the blue here and approach the blue here. Now our oblique asymptote will affect it, but not in this picture. It would be up here somewhere. We would have a graph that's coming down and then go back up according to the blue and pink lines, and another one in the bottom corner that you are not able to see. The domain in this case, there is no holes, so it will just be our asymptotes again. So the domain, x cannot equal negative 4, and x cannot equal 3. Now we're not going to finish the entire last example, but when we do factor this, multiplies to get negative 15 is going to give us a positive 5 and a negative 3. When we factor the denominator, we're going to have x plus 4 and x minus 3. So the only difference here is we find our holes first. We will have a hole where x is equal to 3. You will have a hole in your graph. You will not have an asymptote there, but it will be a hole, and so you cannot have a domain of x equals 3. The rest of it we're going to graph the same way. Just on your graph, when you get to the negative 3, in your final graph, there will just be a hole in that location. So our graph is actually going to approach negative 4. And it'll approach this way, but we have an open circle at 3, because it is a whole, but the rest of our rules will apply the same to this example.